All right, ready for another deep dive?
Absolutely. Let's do it.
Today we're tackling something I bet you encounter every single day without even thinking about it. The combustion chamber.
Yeah, pretty much anywhere there's an engine, there's a combustion chamber working its magic.
It's where the whole fuel-to-motion thing happens.
You got it. The real heart of the action.
We dug into some excerpts from Wikipedia about it, and there's some really cool stuff about how this seemingly simple space has evolved over time.
Oh, yeah. It's way more complex than most people realize.
Let's fire up this deep dive and see what we can learn.
Sounds good to me.
Okay, so first things first. I was checking out the Wikipedia article on combustion chambers, and it mentions they're not just in cars. They're in steam engines, too. Did you know that?
Yeah, I guess that's right. The term combustion chamber can be a little tricky. It's not always talking about the same thing.
Yeah.
For a steam engine, the combustion chamber is more like an extension of the firebox. Helps burn the fuel better, but it's not really containing an explosion like you'd see in a car engine. It's all about efficiency, even way back then.
Huh. Well, for this deep dive, I think we should stick to the internal combustion kind. You know, car engines, that sort of thing.
Definitely. Those are the ones most people think of.
Okay, so internal combustion. That means the burning happens inside the engine. I guess that makes sense.
Yeah, exactly.
And Wikipedia says that's different from an external combustion engine.
It is. Think of something like a steam engine, like we were just talking about. The
Okay.
fire heats up the water outside the engine.
To create steam pressure, right?
Exactly.
Yeah.
That pressure then drives the engine, so it's an external process.
Right. So internal versus external.
Mm.
Totally different ways of turning heat into motion.
Absolutely. And the pressure thing is a big deal, too. The article mentions a difference in pressure between internal and external combustion, right?
Yeah, something about how force is made.
Well, in an internal combustion engine, the pressure from burning fuel directly pushes on parts of the engine.
Like the piston in your car.
Yeah, that's a good example. But in an external combustion engine, the heat first has to be converted into pressure somewhere else, and then that pressure is used to drive the engine.
Interesting. Okay, so let's talk types of internal combustion engines. I see spark ignition and compression ignition mentioned. What's the difference? Those sound kind of technical.
Well, spark ignition is your typical gasoline engine. You have a spark plug that creates a spark,
Okay.
and that spark ignites the fuel and air mixture, which causes, well, the explosion that powers the engine.
Got it. And compression ignition, is that like a diesel engine?
Exactly. In a diesel engine, you use incredibly high pressure to heat the air inside the cylinder, and then when you inject the fuel into this hot, compressed air,
It just explodes on its own.
pretty much no spark needed.
Wow, that's intense. I guess that's why diesel engines sound so different.
Yeah, it's all about that pressure.
Okay, I'm starting to get this. Now, the Wikipedia article mentions that the shape of the combustion chamber matters a lot, especially for those spark ignition engines. Like, why is that?
You know how you have to arrange wood in a fireplace just right to get a good fire going? It's kind of like that. The shape of the combustion chamber is all about creating swirl and turbulence in the fuel-air mix.
Really? Like, specific shapes do that?
Yeah, there are lots of different shapes they use. Hemispherical, wedge-shaped, not even kidney-shaped. Each one creates a slightly different flow pattern, and that better mixing leads to a more efficient and powerful combustion.
So it's all about getting the most bang for your buck, fuel-wise.
You got it. And then they even mention this thing called squish.
Squish. Okay, now you got me curious. Is the fuel literally being squished?
Pretty much. As the piston moves up, it squeezes the fuel-air mix right before ignition, making it even denser.
Ah, so it's like squeezing all the good stuff out of it.
That's a great way to put it. And
Yeah.
then, of course, where the spark plug sits is super important, too.
Right, that's what sets the whole thing off.
Exactly. The spark plug's position determines where the flame starts and how it spreads throughout the chamber.
I can see how that would matter.
If the spark plug's in the wrong spot, you get incomplete burning and less power, so it's got to be just right.
So moving on to compression ignition. How are those combustion chambers different?
Well, remember, they don't have spark plugs, so it's all about using that super hot compressed air to make the fuel ignite.
Right.
And there are two main types they use, direct injection and indirect injection.
So what's the difference?
Direct injection is pretty straightforward. You inject the fuel directly into the main combustion chamber.
Seems pretty efficient.
It is. But then you have indirect injection, which is a little more roundabout.
Roundabout how?
Instead of going straight into the main chamber, the fuel is first injected into a smaller chamber, like a pre-chamber.
Pre-chamber.
Yeah. And then it goes from there into the main chamber. It's a way to create a smoother, more controlled burn, especially at lower engine speeds.
I see. So kind of like a two-stage process.
Yeah, exactly. And while I was reading up on this, I came across a name I thought you might find interesting. Harry Ricardo.
Harry Ricardo. Who was he?
Well, he was a brilliant British engineer, kind of obsessed with engines, especially diesel engines. Back in the early 20th century, he basically revolutionized combustion chamber design.
Really? How so?
He came up with this thing called the swirl chamber.
Swirl chamber, like
Yeah.
swirling.
Exactly. The shape was designed to make the air and fuel mix swirl together more efficiently, and that led to huge improvements in diesel engine power and efficiency.
Wow. So his work is still impacting how we drive today.
Absolutely. He was a real pioneer. And speaking of pioneers, we can't forget about gas turbines.
Oh, yeah. Those are the engines used in jet planes, right?
That's right. And their combustion chambers are a whole different beast.
How so?
Well, in a gas turbine, the combustion process is continuous. It's not like a piston engine where you have these discrete explosions.
Oh, so it's just constant burning.
Pretty much. Fuel and air are mixed and burned continuously, creating this powerful stream of hot gases. And that spins the turbine, which is what creates the power.
Wow. So there's like a controlled nonstop explosion.
You could say that. And the chambers they use are called combustors. They have to be specially designed to handle this constant flow of energy.
So it's not just about containing an explosion, it's about managing it over time.
Exactly.
Okay, we've covered a lot of ground with internal combustion, but let's go back to steam engines for a sec. Remember, the Wikipedia article mentioned they have combustion chambers too.
Right. But in steam engines, the combustion chamber isn't about containing a big explosion like we've been talking about. It's more about making sure the fire burns as efficiently as possible to heat the water and create steam.
So it's like the difference between a furnace and a bomb.
That's a good way to put it.
Okay, one last thing from the Wikipedia article that caught my eye. Microcombustion chambers. Those sound tiny.
They are. Microcombustion chambers are a fairly new area of research. These things are seriously tiny, sometimes smaller than a grain of rice.
What? So small. What are they used for?
They're still mostly in the research phase, but the potential is huge. Because they're so small, they have a really high surface area to volume ratio, and that actually makes combustion more stable and efficient.
Wait, so smaller is better in this case?
It can be, especially for small devices. These microcombustion chambers could revolutionize everything from portable electronics to micropower generation. Imagine a world where your smartphone could run for days on a single drop of fuel.
Whoa, that's crazy.
I know, right? But there are still some challenges they need to overcome, like heat loss is a big one because they're so small.
Makes sense. It's harder to keep something tiny hot.
Exactly. And then finding the right materials that can withstand the heat and pressure in such a small space, that's tough too.
So it's like trying to build a super efficient tiny furnace.
Pretty much. But if they can crack it, microcombustion could change the world. Welcome back for more combustion chamber talk.
Yeah, I'm ready to dig deeper into the design side of things. It's amazing to me that it all starts with this one little space.
I know, right? You don't always think about it, but all that power, all that torque.
It all comes down to what's happening in the combustion chamber.
Exactly, and how efficiently you can burn fuel in there.
Well, the Wikipedia article mentions a whole bunch of different shapes for these chambers. Hemispherical, wedge-shaped, even kidney-shaped. It's wild.
Yeah, each shape has its own pros and cons, its own quirks.
So, what makes a hemispherical combustion chamber so special? I hear that one a lot.
Well, think of it like this. It's kind of the gold standard for efficient burning.
Really? How come?
The shape, it's like this compact dome, and that allows for really good airflow and flame propagation.
So everything mixes together really well.
Exactly. You get a nice even burn. That's why you often see hemispherical chambers in high-performance engines.
So if you want power, go hemispherical. Got it. What about those other shapes? What's the deal with the wedge-shaped one?
The wedge-shaped chamber. Oh, that one's like the workhorse. You see it in a lot of modern engines.
Really?
Yeah, it's not quite as fancy as the hemispherical design, but it still gets the job done.
Hey.
It's good at creating swirl and turbulence, and it's relatively cost-effective to manufacture.
So good balance of performance and affordability. What about that kidney-shaped one? That sounds kind of weird.
The kidney-shaped chamber, huh? Yeah, that one's kind of a blast from the past.
Oh, they don't use it anymore.
Not really. It was an attempt to improve combustion efficiency, but it didn't really catch on.
So it's like a combustion chamber fashion faux pas.
Pretty much. Some designs just work better than others, and the kidney shape just didn't make the cut. But, all this talk about shapes, it really highlights one key thing. The better you can burn fuel, the more power you get and the less you waste.
And that's good for both performance and the environment, right?
Absolutely. Cleaner burn means fewer emissions. And that brings us back to that squish thing we were talking about earlier.
Oh, yeah, squish. Sounds so funny, but it's actually really important.
It is. Remember, squish is all about squeezing that fuel-air mixture right before ignition.
Like giving it a good hard hug to make sure everything's mixed together.
Exactly. And that leads to a much more powerful and controlled explosion. And a cleaner burn, too. Less of that unburned fuel going out the tailpipe.
It's amazing how much thought goes into something as seemingly simple as burning fuel. Like, it's not just fire, it's science.
It really is. It's like designing a tiny high-tech furnace. You have to get everything just right to optimize performance and efficiency.
Speaking of high-tech, can we talk more about those micro-combustion chambers? Those tiny things still blow my mind.
Oh yeah, those are fascinating. It's like shrinking down all that power and efficiency into something the size of a grain of rice.
And you're telling me those could actually power things?
Yeah.
Like real devices?
Potentially, yeah. Imagine your smartphone running for days on a tiny drop of fuel. That's the kind of thing microcombustion could enable.
It's like something straight out of a science fiction movie. But I imagine there are some serious challenges to making something that small actually work.
Oh, definitely. One of the biggest hurdles is heat loss.
Because they're so small, they lose heat quickly.
Exactly. And that can really mess with efficiency. So engineers are working on all sorts of clever ways to minimize those heat losses.
Makes sense.
Yeah.
What about the materials? I bet those tiny combustion chambers have to withstand some extreme conditions.
You bet. Finding materials that can handle that intense heat and pressure in such a small space, that's a huge challenge.
So material science is going to be key to making this whole thing work.
Totally. And, you know, it's just one example of how different fields of science and engineering all come together to solve these big challenges.
That's what makes it so exciting, right? Like, who knows what amazing breakthroughs are just around the corner?
Exactly. That's the beauty of research and development.
All right, so we've talked about the past and the present of combustion chambers. But what about the future? Where do we go from here?
Well, the future of combustion, it's a hot topic these days, both literally and figuratively.
Nice one. But seriously, there are some big challenges ahead when it comes to energy and the environment. How does combustion chamber design fit into all of that?
Well, think of it this way. Those challenges are actually opportunities. Opportunities for some serious innovation.
Okay, I like that perspective.
Because combustion engines, they're not going away anytime soon. We rely on them for so much. So the focus now is on making them cleaner, more efficient, and just better all around.
So pushing the boundaries of what's possible with this technology.
Exactly. And one of the biggest areas they're working on is emissions, obviously.
Right. Got to make those engines cleaner.
We've already made huge strides in reducing the harmful stuff coming out of tailpipes.
Yeah, cars today are way cleaner than they used to be.
Right. But we can't stop there. The goal is to make combustion even cleaner while still keeping the performance and fuel efficiency that people expect.
So it's a balancing act.
Absolutely. It's a tough challenge, but engineers are working on some really cool stuff.
Like what? What are some of the things they're trying?
Well, one really promising area is something called HCCI, stands for Homogeneous Charge Compression Ignition.
HCCI. Okay, now that sounds complicated.
It is pretty complex, but also super interesting. Basically, HCCI is like combining the best of both worlds.
What do you mean?
Well, in a regular gasoline engine, you mix the fuel and air pretty thoroughly before ignition, and that helps with a clean burn. But then you have diesel engines, which use compression ignition. That's super efficient.
Right. So HCCI is like a hybrid.
Exactly. It's like taking the efficiency of a diesel and the clean burning characteristics of a gasoline engine and putting them together.
Wow, that sounds amazing. So what's the catch?
Well, there are still some technical hurdles to overcome before it's ready for prime time. Controlling the combustion process precisely, especially under different conditions, that's still tricky.
Makes sense. What about fuels themselves? Are we going to be using gasoline and diesel forever?
Not necessarily. There are lots of researchers looking into alternative fuels for combustion engines.
Oh yeah, like what?
Well, biofuels are getting a lot of attention these days. Those are fuels made from plants or other renewable sources.
So instead of digging up fossil fuels, we could just grow them.
Pretty much. It's a really cool idea, and there are already some biofuels being used in cars today.
Oh, neat. Anything else on the horizon?
Oh yeah, there's also hydrogen. It burns super clean, only producing water as a byproduct, no harmful emissions at all.
Wow, hydrogen sounds like a game changer.
It could be. But there are still challenges with hydrogen, mainly storage and transportation. It's tricky stuff to work with.
So there's a lot to figure out with alternative fuels.
Definitely. It's not just about the engines, it's about the whole fuel system. But the good news is there are a lot of smart people working on it.
Okay, so new engine designs, new fuels. It's almost overwhelming, all the things they're trying to improve.
But right? It's a complex puzzle, but that's what makes it so exciting.
True. And we don't have to solve it all overnight. Every little improvement gets us closer to a better future.
Exactly. It's all about progress, step by step.
Well, before we wrap up, I got to ask you about those micro-combustion chambers one more time. What do you think the future holds for those tiny things?
Those little guys. I think they have the potential to be huge. Literally.
Okay, how so?
Think portable power. Imagine your smartphone, your laptop, even medical devices in remote areas.
All powered by these tiny combustion engines.
Exactly. They're silent, they're efficient, and they could run for a really long time on just a little bit of fuel.
That sounds amazing, but we talked about the challenges earlier, like the heat loss and the materials.
Right, those are still hurdles. But I'm optimistic. I think as we develop new materials that can handle those extreme conditions, the possibilities for microcombustion will really explode.
Well, you've given us a lot to think about today. Any final thoughts you want to leave our listeners with?
Yeah, I think the biggest takeaway is this. Combustion might seem like old technology, but it's far from dead. It's constantly evolving, getting cleaner, getting more efficient, and playing a huge role in our energy future.
That's a great point. So next time you hear an engine roar to life, remember all the amazing engineering and innovation that went into making it work.
Exactly. It's a testament to human ingenuity.
Well, thanks for joining us on this deep dive into the world of combustion chambers. Until next time, keep those minds curious.